Okay, thank you. This is Man Fai Ho. Today I will present the paper of decomposition, the origin of TeV to PeV emission from the Galactic Plane, implication of multi-messenger observation. Here's the agenda, and I will cover what is the multi-messaging approach, motivation, result, why comes this paper, physics behind, implication, and lesson learned. As usual in physics, experiment data is the key to understand how to produce high energy cosmic ray. What is the origins, its composition, and energy spectrum? Different cosmic ray particles will have a different production and propagation mechanism. That's why we have the approach using the following messengers mixed together for a study. Cosmic rays, charged particle, most of the time is deflected by the magnetic field, affecting their path, so difficult to point to the source. But when the energy above the tens of eDV, it can be pointed. Gamma rays definitely point to the source easily, but unfortunately absorbed and recreated by multi-emission mechanisms. Gamma ray has transparency in most of the region up to some 100 GeV. But beyond this energy, the interaction with the background photon, like the CMB, will have absorption effect. Through the interaction, photon to a pair of electron and positron, impacting its propagation. Neutrino, favorite interaction, neutral property. So easy point to the source. It provides very good information from deep within the origin. Detection is very difficult, but this is not worse. Finally, gravitational wave is a new and good tools, but unfortunately not in the scope of this paper. Based on the nature of those messengers, using neutrino for cosmic ray study is much more effective than high energy gamma rays. Actually, neutrino produced by cosmic wave reaction can get more important information about the source that is not easy to access. But please be aware, neutrino sources also have a similar nature with the photon source as well. So the analysis to map out neutrino spectrum is very important, supporting with the existing gamma ray data, which can help to constrain possible neutrino flux for further study. Is really the objective for this paper. So the motivation for this paper is mainly to evaluate galactic diffuse emission, GDE, and high energy neutrino flux from different emission sources in Milky Way based on up-to-date gamma ray observations. Using multi-messaging model, they call it connection model. The model will leverage gamma ray catalogs and use their source measurement and observation of GDE to derive the maximum flux of neutrino emission from the Galactic Plane, GP, to find out more about the source information. Here is the key result from the paper. First, ice cube galactic neutrino flux is larger than the contribution from all resolved sources, especially not including lone leptonic sources, such as pulsar, libellate, halo. Second, galactic neutrino emission is dominated by diffusion emission in two parts. One is a cosmic ray C, another is the unresolved hadronic gamma ray sources. Third, from ice cube flux data, the paper told us the source may be either as a truly diffuse emission or unresolved hadronic emitter. This paper wants us to understand galactic plane and disentangle the contribution of individual sources from those diffuse emission, even in PeV gamma ray contribution like the pivoton and the leptonic source. The author knew their final goal is to detect individual galactic neutrino sources directly. But this is the goal, not on the result from the paper. So they only take the first step to understand the source contribution to the neutrino GDE, then derive the neutrino flux, just only these two things. Then wait for the future observation. Okay, quickly back to the physics. Most of the cosmic ray is proton, and small portion is electron. From the paper pursuing the origin of the gamma rays, you can see it is very clear the gamma ray emission is produced by two quite different processes. One, cosmic ray electron through the inverse quantum scattering, ICS. Another is a cosmic ray protons and nuclei, then generate charged and neutral pion. Neutral pion then decay into the gamma ray as well. But high energy neutrino can only come from the proton and nuclei, in particular with charged pion decay. These are the most important process, and we need to know. The problem, if the proton generate the gamma ray, then we can directly verify the origin of the cosmic ray. Our job must be easy. But gamma ray are also produced by electron through the ICS. So we need to find out which is the proton origin or electron origin, as well as measure the ratio of these two contributions. That's the reason we need neutrino altogether in order to differentiate these two processes of gamma ray production in cosmic ray. Okay, so many terms. What is galactic diffuse emission, GDE? In simple, cosmic ray collide with gas in ISM and produce charged and neutral pion, kind of meson. Then decay into a neutrino and gamma ray respectively. These secondary particles form the region that we call as GDE. One more point. From our reference book, Cosmic Ray and Particle Physics, it highlights close to 100% this secondary particle is to be produced by the pion more than a kaon. Aside from this GDE, we really want to study what kind of the potential sources, maybe hadronic or leptonic, even other like dark matters. For hadronic source like the supernova, you can see there's many different processes in the quantum. When the proton or other nuclei hitting into other nuclei or low energy photon, gamma rays must be a byproduct of the reaction. For leptonic source like the pulsar, halo, they also have many different reactions. The main emitter must be electron, producing gamma ray through the scattering of low energy photon, CMB. From the same author, Fan, for another paper, multimessenger implication of sub-PeV, diffuse galactic gamma ray emission. They have a chart on the top right-hand corner. GDE at GeV TeV energy range is expected to be contributed by neutral pion decay of a hadronic cosmic rays, which is the majority contribution, more than the inverse quantum emission by electron, which is just a minor contribution. I also find out some more information as a supplement for this ratio from another paper qualifying the hadronic and leptonic components. During the study on the supernova Rami, the proton are the reason for almost 70% gamma ray emitted from the cosmic ray. Electrons just only 30%. From another paper, high energy neutrino from the cosmos by Francis. They point out the main challenge is to separate this gamma ray from proton source or electron source. But we know neutrino are accompanied by gamma rays. So the studying with the neutrino altogether can help us to know more about the source in much more clear. And that's why multi-messaging approach is important. Although most of the pion production should be from hadronic source, this is not a certain. From another interesting paper I found, TeV neutrino can also come from energetic electron through the electromagnetic interaction in different potential cosmic ray sources, with flux level similar to that from the hadronic at high energy. Actually, at above certain thresholds, the energy of the muon-pion pair production, the interaction of electron with radiation field, means the photon, can also generate a pair of a muon, even pion, and an electron, then decay into neutrino. So pion production can come from leptonic source. This is not the further study. Okay, where does the major neutrino come from? The paper set is from the Galactic Plane, GP. That's why they study GP. Neutrino from the GP may come from two components of the galaxy. One is the cosmic ray C, another is the individual sources. Cosmic ray C is another important source, which is smooth, steady distribution of the cosmic ray propagating in the kinetic magnetic field. Proton and nuclei at TeV and PeV energies will confine in kinetic magnetic field and lose their initial direction. Again, hadronic pion is not the only process for gamma ray. For leptonic electron also upscalar CMB to gamma rays. From the calculation using the root mean square propagation distance, we can also confirm electron above 10 of TeV cannot travel too far away from the source. Okay, back to the model we love from the research. As I mentioned, cosmic neutrino are accompanied by high energy photon. Neutrino and gamma ray are definitely connected with some relationship when we study the source. This paper leveraged the model they call as a multi-messaging connection model to differentiate the neutrino and gamma ray in hadronic PP scenario. From the reaction, you can see neutrino production ratio is the 3 times of pion. Similarly, pionic gamma ray production rate is 2 times of neutral pions. So neutrino energy spectrum can be derived as 3 to 2 pionic gamma rays. For the energy side, considering the ratio of charged and neutral pions is approximately 2 to 1 at high energies. Gamma rays and neutrinos carry on the average 1 to 2 and 1 to 4 of the energy of the parents pion as well. That helps to form the first relationship between the neutrino and gamma ray from the pion production. Then adding kinetic coordination system into the model, we can come up the probability of the interaction using the optical depth, then calculate the average gamma ray intensity from a region of solid angle, as well as all the favor for neutrino together. The calculation is kind of similar to our homework, except we did not use the kinetic coordinate system. This is all the detail coming from the same author of his previous paper, multi-messenger implication of sub-PeV diffuse kinetic gamma ray emission. That's the reason we need to study 2 papers at the same time in order to understand the model clearly. Then putting all together, the model can successfully come up with this relationship in mathematical structure here. So this mathematical structure can effectively model the connection between the gamma ray and neutrino emission through the hadronic process in galaxy, not include leptonic. Based on gamma ray observation data in GDE, it can subsequently derive the upper limit on the kinetic neutrino flux expected from the resolved sources and GDE. Okay, the implication. From the observation, the neutrino contribution from resolved gamma ray sources, not include those associated with the pulsar, is smaller than the ice cube kinetic neutrino flux measured with neutral pion template by a factor of around 2. It tells us the neutrino emission could be dominant to be produced by the diffuse cosmic ray or unsolved source from the gamma ray observation. At around 1 to 30 TeV, the sum of the resolved non-pulsar sources and the LASO diffuse emission is quite similar with that of the ice cube neutral pion flux when assuming 100% hadronic. This indicates LASO diffuse gamma ray emission could not be dominant by unresolved leptonic sources such as TeV halo. At around 30 to 100 TeV, the neutrino flux measured by ice cube is also similar, even higher than that derived from the Tibet AS gamma GDE. They tell us it may be a hadronic origin of the GP gamma ray emission. At around 100 TeV above, GDE is dropping due to the cosmic ray needs. If GP neutrino and gamma ray spectrum extend to the higher energy without a break, they believe this is contribution from super perphetron, such as hypernova Rami and super bubbles. So, come to the lesson learned. Right-hand side diagrams is all about the physics behind in summary, with more of the key process in cosmic ray, even what is the problem in gamma ray observation and why we need the neutrino together. Actually, here are some key points and very important process we need to know before study the papers. First, the first key point is we need to know the identification and measurement of the kinetic neutrino sources or gamma ray sources. It's required to have a separation of GDE component. One is cosmic ray C, another is a source itself. Second, when using gamma ray observation data, multi-messenger connection model teach us how to connect between the kinetic neutrino and gamma rays. Lastly, from all the observation data, the result confirm kinetic neutrino is dominant, which is produced by diffuse cosmic ray or unresolved sources. So the author believes upcoming much more advanced neutrino telescope like the KM3NET and IceCube Generation 2 can help to resolve more about the individual kinetic source. And finally, disentangle the source emission and GDE. Okay, this is the end of my presentation. Thank you. And welcome for the question that I can follow up maybe through email. Thank you very much.